In our previous lectures, we have seen linear differential equation of two types. The first one was dy by dx plus py equal to q, and the second one was dx by dy plus p dash x is equal to q dash. Now in today's lecture, we will move ahead with the last type of differential equation, which is called the Bernoulli's differential equation. Now, we have also seen one more type, which was called as differential equation reducible to linear differential equation form. Differential equations which are reducible to linear differential equation forms. In that, what we did was, we have to identify the function and its derivative present in the differential equation. On the same grounds, we have to learn the Bernoulli's differential equation. Now, the change in the previous type, that means the reducible type, and the Bernoulli's differential equation is very small. In Bernoulli's differential equation, you will find only algebraic terms. There will be no other term, no trigonometric, no exponential, no logarithmic terms. Only and only algebraic terms. A Bernoulli's differential equation can be seen like this. Observe carefully. When I have dy by dx plus py equal to q, we all remember in dy by dx plus py equal to q, y is called the dependent variable, whereas x is called the independent variable. And p and q are both functions of x. So this we are going to maintain. Our dependent variable is going to be y. Our independent variable is going to be x. P and q are definitely going to be functions of x. So we are going to maintain this particular terminology. But there will be a small change in the equation. Observe what change you will find. A Bernoulli's differential equation will look something like this. Dy by dx plus py is equal to q. So you might expect what change is there. See, dy by dx plus py is equal to q. It is exactly same. So what change that you will find is, you will have y raised to n on the right hand side. So whenever you get a differential equation in which you want or you see a power of y, you can see power of y. So whatever highest power of y you can find, the highest power of y will be always kept on the right hand side. Always keep the highest power of y, and you remember that y is your dependent variable. That means the highest power of the dependent variable is maintained on the right hand side. So y raised to n is kept on the right hand side. The next thing that you should be doing is divide the entire equation. This entire equation will get divided throughout by the highest power of y, which is y raised to n. So I'm going to divide the entire equation throughout by y raised to n. So if I divide the entire equation throughout by y raised to n, see what changes I'll be getting. So dividing throughout by y raised to n, the first one becomes 1 upon y raised to n, and then I'll write dy by dx. Then plus p, y gets divided by y raised to n. So y in the numerator, y raised to n in the denominator. So one of the y will get cancelled, and I will be getting 1 upon y raised to n minus 1 is equal to q. Now if you observe, q is entirely a function of x. So now q is isolated completely. It exactly represents my linear differential equation. Right hand side is a function of x. Now my worry is about this term, 1 upon y raised to n minus 1. Now I hope everyone remembers that the derivative of x raised to n, is given by n x raised to n minus 1. You all remember it from derivatives concept. So derivative of x raised to n, x raised to n minus 1. So if I ask you derivative of 1 upon x raised to n, so derivative of 1 upon x raised to n will simply become d by dx of x raised to minus n. That means I have taken the term in the denominator into the numerator by using the law of indices. So x raised to minus n. And now if I apply the derivative formula, it becomes minus of n. It looks like x raised to n. So minus of n, x raised to this minus 1, minus n, minus 1. Or I can simply say minus of n. This will come down the denominator. I get x raised to n plus 1. So that's the formula that you should always remember for derivative of 1 upon x raised to n. So now if I come here, if I look the terms over here, I have 1 upon y raised to n minus 1. What I will do here is I am going to substitute this 1 upon y raised to n minus 1 as v. Let's substitute our dependent variable, which is y. So 1 upon y raised to n minus 1 with a new dependent variable, which is v. So 1 upon y raised to n minus 1 is taken as v. More important now, this is the most important part that we should always remember. I'm going to differentiate both sides. Let's differentiate both sides. See, you are changing from a variable y, which was your dependent variable. So you're changing from the variable y to a new variable v. So dy by dx should also change. Y is getting replaced into v. So dy by dx should also change to dv by dx. So whatever this thing I have taken the substitution, I'm going to substitute 1 upon y raised to n minus 1 as v. So y is getting changed into v. So dy by dx should also change into dv by dx. So dv by dx means you should differentiate with respect to x. So let's differentiate both sides with respect to x. So if I differentiate both sides with respect to x, see now this looks like my formula. The formula says minus of n upon x raised to n plus 1. Minus of n means take the power, write in the numerator, put the minus sign, and upon x raised to power plus 1. Here the power is n minus 1. 1 upon y raised to n minus 1 we have. So the power is n minus 1. So I write minus of n minus 1 upon power plus 1, n plus 1, x raised to n. I had power plus 1 in the answer, n plus 1. So here n minus 1 plus 1, power plus 1, I get y raised to n. Since it is a term of y, we are differentiating with respect to x. A term of y getting differentiated with respect to x will give us dy by dx. Very important. Y is getting differentiated with respect to x, that is why this dy by dx has come, is equal to dv upon dx. So now if I observe my equation, I can do some small changes. Let's see what changes I will be getting. Observe the changes. So in my equation I have 1 upon y raised to n dy by dx. This minus and n minus 1 is an extra term. I should get rid of these constants from here. N minus 1 is a constant term. Negative sign is a constant term. Let's remove these terms from here. They are on the left hand side. They are in the numerator. So when they go on the right hand side, they go in the denominator. That means I can say 1 upon y raised to n minus 1 dy by dx will become equal to, the minus n goes on the right hand side, you get minus, the n minus 1 goes in the denominator, so 1 upon n minus 1 and dv by dx, and dv upon dx. So that's the replacement available for 1 upon y raised to n minus 1 dy by dx. Similarly, for this term, the replacement is here, 1 upon y raised to n minus 1b. Let's rewrite the entire equation. So now if I rewrite the entire equation, I can write for this term, I have the replacement over there, so I write minus of 1 upon n minus 1 dv upon dx. Then plus p into, this term is taken as v from the substitution. So p into v is equal to q. Still it is not representing my original differential equation, isn't it? The original differential equation should not be accompanied, this dy by dx should not be accompanied with any number over here. No coefficient should be present. So over here I see dv by dx is accompanied with some number. Let's get rid of that number. Multiply this entire equation throughout by negative sign and n minus 1. So if I now multiply throughout by negative and n minus 1, I get dv by dx. I write a plus sign only here, and then I write minus of n minus 1 into p, and then I write v. Observe carefully how the arrangement is done. So the negative sign has come here, and then n minus 1 also has come here, and p. This entire thing is taken together. V is equal to minus of n minus 1 into q. Let's take this also an entire single term. So now if you observe this equation, it now exactly resembles dy by dx plus py is equal to q, our original linear differential equation. Now for this, we all remember that the integrating factor, if you remember integrating factor, it is given by e raised to integration of p. So in place of p, see what do you have? In place of p, you have minus of n minus 1 into p. So you get minus of n minus 1 into p dx. That is how we get the integrating factor. Then to get the solution, again you must remember, to get the solution, we write the dependent variable. Now observe carefully, your equation is dv by dx. dv by dx, the dependent variable is v, so I write v into the integrating factor. Over here you are going to get the integrating factor. So v into the integrating factor is equal to integration of the right hand side of your differential equation. This is your differential equation. I'll mark it out over here. This is your differential equation. You will take the right hand side of this differential equation, and that's minus of n minus 1 into q. That's the right hand side of the differential equation. Multiply with the integrating factor, whatever it is, and dx plus c. So that's how I get the solution of the differential equation, the Bernoulli's differential equation of the first type. So Bernoulli's differential equation, the first type, dy by dx plus py is equal to q, y is to n. Y was your dependent variable. Y is the dependent variable. So the highest power of y is maintained on the right hand side. Y is to n is maintained on the right hand side. So now when I go to the next step, which is dx by dy plus p dash x is equal to q dash. Dx by dy will have x as the dependent variable. Y is your independent variable. So when you go to the Bernoulli's differential equation, the equation would look something like this. Observe carefully. We can correlate the things from here itself. Dx by dy. So I get same dx by dy as it is dx by dy plus p dash x. Same things, isn't it? Is equal to. This is where I should be very careful. Q dash, and the next term that I'll be getting is x raised to n. Likewise here, I had y raised to n because y was my dependent variable. In this case, x is my dependent variable. So I get x raised to n. So dx by dy plus p dash x is equal to q dash x raised to n. Exact same steps will be repeated for this type also. That's the second type of Bernoulli's differential equation. Here what I did, I divided through by minus 12. Y was my dependent variable. Here x is my dependent variable. X raised to n, the highest power is maintained on the right hand side. So I'm going to divide throughout by x raised to n. I get 1 upon x raised to n, and then dx by dy, and then plus p dash. X gets divided by x raised to n. So x in the numerator, x raised to n in the denominator. So one of the x will get cancelled, and you will get 1 upon x raised to n minus 1 is equal to q dash. I hope you must be definitely remembering that p dash and q dash, they are both functions of x. Isn't it? Sorry, they are both functions of y. So p dash and q dash both must be functions of y. So dx by dy plus p dash 1 upon x raised to n minus 1, that's my worry at this moment, is equal to q dash. So now this q dash and this q dash, they are both same now. So it now looks like more or less like my differential equation. So q dash is a function of y. I have isolated that term. Now my worry is again this 1 upon x raised to n minus 1. Not a problem. I already know how to differentiate 1 upon x raised to n. I know how to differentiate 1 upon x raised to n. The derivative is minus n, the power, upon x raised to n plus 1, the power plus 1. So here if I take 1 upon x raised to n minus 1, 1 upon x raised to n minus 1 as v, that's my substitution. 1 upon x raised to n minus 1 as v, and if I differentiate both sides with respect to, very important, with respect to y, because you get dx by dy, y is your independent variable, so you have to differentiate this with respect to y. The reason, dx by dy, x was dependent variable, x is getting substituted into v. If x is getting replaced with v, dx by dy should get replaced with dv by dy. Now how it is done? It is done from the substitution. I'm going to differentiate both sides. So differentiation should be carried out with respect to y. So if I differentiate both sides with respect to y, here the power is n minus 1. So minus of n minus 1, x raised to power plus 1, the derivative suggests me power plus 1, n minus 1 plus 1, that becomes n. Since it's a term of x and we are differentiating with respect to y, that's why we will be getting dx by dy. A term of x getting differentiated with respect to y, so we get dx by dy is equal to dv upon dy. So now if I observe my equation 1 upon x raised to n, I have 1 upon x raised to n. So what I need to remove from here is a negative sign, the n minus 1. Let's get rid of these two constants. So I'll be getting 1 upon x raised to n dx upon dy is equal to, so remove the negative sign, goes on the right hand side, still remains negative, n minus 1 in the numerator, goes on the right hand side, goes into the denominator. So 1 upon n minus 1 dv upon dy. So when I go back to my equation, this term can be replaced with the substitution 1 upon x raised to n dx by dy is this substitution. I'm going to replace this term over here, and this particular term is my substitution 1 upon x raised to n minus 1 is b. So let's get back to the differential equation, do the substitutions and rewrite the differential equation. What do I get? Let's see what do I get. So the first term becomes minus of 1 upon n minus 1 dv by dy. Minus of 1 upon n minus 1 dv upon dy. Then the next term is plus p into, this is v. So I write plus p into v, isn't it? And is equal to q dash, is equal to q dash. That's p dash and q dash. This is p dash. Now, if I want to compare my differential equation with the basic type, dx by dy is a single term, is an alone term. It is never accompanied by any number, any function. So I need to get rid of the negative sign and n minus 1. Not a problem. Multiply the entire equation throughout by the negative sign. Multiply the entire equation throughout by n minus 1. So when I change this equation, if I multiply this equation with negative sign and n minus 1, first of all I will be getting dv by dy. I am multiplying with the minus sign. I will write plus in between first of all. Then I write the negative sign. Then I write the n minus 1. And then I write the p dash. And I keep them together, all of the terms, into v dash is equal to the negative sign, the n minus 1 into q dash. Again, you keep these terms together. So now, if you observe, this definitely looks like your differential equation dx upon dy plus p dash x is equal to q dash. See, dx by dy, dv by dy plus p dash. This entire thing is a value of p dash. X, this is x here. X was the dependent variable. V is the dependent variable. So I get v over here is equal to q dash. So this entire thing is taken as q dash. Next, obviously, we all know. First of all, I need to get the integrating factor. It will be given by e raised to integration of. For this, it was e raised to integration of p dash dy. For this differential equation, it was p dash dy. So here, I will be getting, in place of p dash, I have minus of n minus 1 p dash. Obviously, dy will come. That's your integrating factor. And finally, when you need to write the solution, it's going to be, first of all, the dependent variable. So that is v. Dependent variable is v. Then you write the integrating factor, which is e raised to, or you can directly write the integrating factor because you have already calculated over here. So I will write the integrating factor over here. If is equal to integration of the right hand side. In our case, the right hand side. So q dash of the right hand side for the basic differential equation. In our equation is minus of n minus 1 q dash. Minus of n minus 1 q dash. That's the right hand side. Multiplies with the integrating factor. This multiplies with the integrating factor dy plus c. So that's my solution. One final thing that we should be doing in both of the solutions. See, my solution was here. In type 1, this is my solution. In type 2, this is my solution. So I should never ever forget to replace the v back into the solution, because v is the term that we have brought in the solution for simplicity purpose. So that is why we have to replace this v back into its original form. So in previous case, in the first type, v, if you remember, v was 1 upon y raised to n minus 1. So what I should be doing is, we should substitute this v 1 upon y raised to n minus 1 back into the solution. In this type, the second type, this v is nothing but 1 upon x raised to n minus 1. So without fail, you should again go back to the solution that you have got and replace this v with 1 upon x raised to n minus 1. So people, This is the way we have to solve a Bernoulli's differential equation. We will definitely be taking some example on this particular concept. Keep watching. Thank you very much.